Hello, my name is Rubi Navarro Alonso, and I'm going to talk about spectrophotometry. I choose this theme because I know this method is one of the most useful methods of quantitative analysis in various fields such as chemistry, physics, biochemistry, and the one I've seen the most is the clinical applications. And one of the clinical applications I think is the most important is the determination of gases in blood. And this method is the most used in this analysis. So I'm going to talk more about it later in my experiment. So let's talk more about what is the spectrophotometry. So the spectrophotometry is a method to measure how much light a chemical can absorb, and we measure the intensity of light that passes through the solution. So this principle is about that each compound can absorb or can transmit light over a certain range of wavelength. So this measurement can be also used to measure the amount of a chemical in a solution, or can be used to detect there is a chemical we don't know about, and can show that a solution has impurities in there. So let's talk more about the diagram, then how a spectrophotometer is composed. Okay, so there is some instruments. We need a light source, a collimator, a monochromator that is a Prims or a grating, a wavelength selector, the cuvette that it has the solution we are going to test, and the detector that it has photocells, and a digital displayer that is going to show you the absorbance. So first, the light source is going to provide the range of wavelength we need. So now that we produce the range of wavelength we need, and the collimator or the lenses are going to transmit a strike beam of light that is going to pass through the prims. So this prims is going to split the, the beam of light into wavelengths. So now that we see the wavelengths, and these are going to have colors that are just like the rainbow, and that's why it's called a spectrum. So now that we have the spectrum that is done by the monochromator, a wavelength selector is going to transmits only the wavelengths we desire. So now we have the desired wavelengths we need. These are going to pass through the cuvette that it has the solution we are going to test, and the photometer is going to detect the amount of photons that were absorbed by the solution, and is going to send a signal to the digital display, and this signal is composed of electrons. Now that we see the measurement in the digital displayer, this is called absorption. And now I'm going to talk more about the applications that this method is useful to. So one of the applications is the concentration to determine to get or detect the concentration of any chemical. We can detect impurities in some solution. We can quantify certain proteins in some compounds. And we can do respiratory gas analysis in hospitals. We can determine the molecular weight of some compounds, and we can also determine or see if there is some compound in a solution or some preparations that we think are pure. And now that we do the spectrophotometry, we can see there's another one that also absorbs the light. And the most important for me is the one that we can determine or we can detect the presence of gases in blood. And these gases are transported by the hemoglobin. So that's why my experiment is about the detection of hemoglobin in blood. If there is hemoglobin, that means the blood has oxygen. So now I'm going to show you this through a virtual laboratory, and now I'm going to show you.
Okay, so my experiment is going to be the use of virtual spectrophotometer to get the concentration of hemoglobin or the observation, because observation and the concentration of some chemicals are directly related. So I already done my solutions. First, we need your blank solution. This consists of only 3 millimeters of water. The second cubit is going to be only 1 millimeter of hemoglobin and 2 millimeters of water. And the third one is the more concentrated, because it has 2 millimeters of hemoglobin and 1 millimeter of water. So we are going to calibrate the spectrophotometer, and we are going to power up. We are going to open the door, and we're going to put the first cubit or the blank inside of the spectrophotometer. So we are going to close the door, and the observance is 0.098. Now that we got the observation, we are going to put out the blank solution. The wavelength of the 3 qubits is going to be 500 nanometers. So now we are going to put the second qubit. We are going to close the door, and the observance is going to be 0.126. And we're going to open, and we're going to put out the qubit. Now we're going to put the solution that is more concentrated, so we expect to get more observance than the two others we got. And we're going to close, and the observance is more with 0.145. And now that we have this, we can get the spectrum of the qubit that it has more concentration, and the spectrophotometer has a software that transfers to the computer and creates their own graphic, and it's a curve, and we're going to open it. This graphic has the wavelength in the bottom, and here we have the observance. Now that we did that, we can erase the results, and as expected, we got the third qubit with more observance. And this is important because we as a chemist, we always do the concentration of hemoglobin when some patient needs to go to some surgery or if they need blood transfusions. So it's common on your daily work, and we finish the experiment just by throwing everything to the chemical waste, and that's it.